Okay.
There we go. That's the remote. Oh yeah, great. Okay.
Okay, so hello everybody. Today's speaker is Cor Kraaikamp from the Technical University Delft. And he will be speaking about natural extensions to the theory of continuous fractions.
Yeah, thank you for the invitation, and it's wonderful to be here. And, wow, it's actually quite impressive, I have to say. I have to warn you though, my talk is going to be extremely easy. So either you fall asleep or you think, wow, finally an easy talk. Okay, so I'm going to talk about natural extensions, and I've been working on this more or less my whole life. Well, not in childhood, of course, but so I'm going to talk about old things and new things. And the new things are with Irene, as you all know. Some of the old things are with Piet Bosma, who's in Nijmegen. He's a very good friend of mine, actually. In the first day I started to study in Amsterdam. And Henk Jager, he's my PhD advisor. There are many more things, but I'm going to talk about continuous fractions. So you very quickly start to talk about the Gauss map, and probably you all know, I've seen it published papers on continuous fractions. So in a way this is a bit superfluous to explain all of this. For me, the way to do continuous fractions is via Euclid's algorithm. If you put it upside down, you get in a natural way, as a generalization, the Gauss map. We all know how it looks like, so I'm not going to make a drawing. And yeah, well, this is also a little bit over the top, but suppose that the floor of x is a0, and I make a number between 0 and 1, which is x minus a0, because the Gauss map only works on the unit interval, and I iterate it. So this t to the power n minus 1 means that I use t n minus 1 times to the point x0. I do 1 over it, take the floor, so this is going to be the partial quotient, or digit, the nth digit, or nth partial quotient, of course. Oops, yeah, nice. And you want to keep it this good?
I really want to know it's better.
Yeah, for me it's nicer for my eyes. Anyway, so what is the idea? Well, t of your starting point is going to be 1 over x0, if your starting point is x0 minus its floor, which we called a1. The same we do with, if we apply it twice, it's going to be t applied to, etc. So it's going to be 1 over the t of x0 minus a2, and you can do this. As long as this is not 0, no problem. And if x or x0 is irrational, then of course all these iterates are also irrational. So this is the irrational number minus a rational actually integer, positive integer. So this is certainly never 0. And why did I do it like that? Well, we defined x0 as x minus a0 to bring it between 0 and 1. So x is a0 plus x0. But x0 is here. So if I bring a1 to the other side and put things upside down and also do it here and do it here, I can replace x0 by 1 over a1 plus the t of x0. But t of x0 I can replace it by 1 over a2 plus t 2 times applied. Well, you can do this as many times as you want if x is irrational. So this number will be 0 if my starting point is rational at some point due to the Euclid algorithm, and otherwise it just will be not 0, go on forever. And this is a really annoying notation, so I write it like this. And yeah, these are called partial quotients. A0 is of course some integer. These are all positive integers. You can also call them digits. And as you can see, the A0 is doing nothing really. So we might as well leave it out. We just work with numbers between 0 and 1. Okay. And Euclid's algorithm tells you x has finitely many partial quotients. So at some point you map t hits 0, if and only if x is a rational number. In general, if I have an expansion of some number x, I can cut it off. I can take like a truncation Of course, this will be 1 over a1 plus 1 over a2 plus up to 1 over an. This is a rational number. So we want to say, like, can we find it easily? We know it's rational, so it's of the form, let's say, Pn over Qn, with Pn and Qn relatively prime. Can we find in an easy way the Pn's and Qn's? Well, you all know it's true. It's very easy to find. And how do we do it? Well, one way to do it is use these matrices. Very simple. I'm not sure who started this. I know that, of course, series looked at these matrices and Elf on the board looked at them. I don't know who did it, but this is really a nice way to get them. Just say this product Mn, we know it's a product of integer matrices, you know, of this determinant. This is 1, of course, and this is minus 1. So I know these Rn, Sn, Pn, and Qn are integers. That's nice. But I know more, because I know that Mn is like Mn minus 1 times An. So I can just write out the product. I know Mn is Rn, Sn, Pn, and Qn. I said it like that. It's 1 before times the An. But yeah, this is a trivial calculation. If you do the calculation, you find that actually Rn is Pn minus 1, Sn is Qn minus 1. And that's something you often have in continuous fraction algorithms, also in multidimensional ones. That the columns before the last column give previous convergence. Right, I still have to show it's a convergence, but that's what it is. But you also see something really nice. Pn is, I can express it in the previous two. It's An digit, the partial quotient, times Pn minus 1 plus Pn minus 2. And the same with the Q's. So are these then, the Pn over Qn, are these the convergence? These are these recurrence relations? Well, the answer is yes. And to see that, we view these matrices simply as fractional linear transformations and Möbius transformations. So, by that I mean A applied to Z is this fraction, A times Z plus B divided by C times Z plus D. Why? Well, I know what Mn is. Mn was Mn minus 1 times this matrix 0, 1, 1, An, and I apply it to 0. If I apply this guy first, I get 0 times 0 plus 1 divided by 0 times 1 plus An. I get 1 over An. So I can repeat this procedure. So if I do it one more time, if I write Mn minus 1 is Mn minus 2 times An minus 1, I get Mn minus 2 times this fraction, and you see it's sort of building up this finite continued fraction. So after n steps, kind of induction. Oh, no problem. I get this thing. But I also have, if I look at this, and I know Mn is Pn minus 1, Qn minus 1 in the first column, Pn, Qn in the second column. If I apply it to 0, I would get Pn minus 1 times 0 plus Pn divided by Qn minus 1 times 0 plus Qn. In other words, I get the second column as a fraction. So I see that Pn over Qn is really this continued fraction. And we find more, because this is a very simple matrix. I see the determinant is, well, this is elementary, right? But it's also the determinant of A1, A0, which is 1 times minus 1 times minus 1 times minus 1 is minus 1 to the power n. So you see that this number is minus 1 to the power n. And that means that if Pn and Qn were not relatively prime, let's say there's a number d larger than 1 dividing both Pn and Qn, it would also divide minus 1, which is impossible. So we right away find, boom, the greatest common divisor is 1. Well, this is stuff you all know, right? I mean, it's trivial. And why is it handy? Well, why did I bring this up? Because I wanted to show you one thing which was actually on the first slide of the Carnot combination. So, boom. I thought, well, let me take a little longer time to get there. If I apply Mn to Tn, what do I get? I have Mn minus 1 times An, which is 0, 1, 1, An. Apply to Tn, so this last thing would be 1 over an plus tn. So actually, this is what you get if you just plug it in, but you also get that it's x actually. And then from this I see that if I take x and I subtract its nth convergent, so x would be this number, that's this one, minus its nth convergence is that, and then you make down the same. So here you multiply with qn top and bottom, here you multiply with qn plus tn times qn minus 1 top and bottom. I get this. Now it's a bit fast, and that I get this down is obvious, but if I multiply here with qn, I get pn qn plus tn times pn minus 1 qn. If I multiply here with qn plus tn qn minus 1, I again get pn qn, but due to the minus sign they will drop out. And I will get tn times pn times qn minus 1. So the tn I can bring outside the bracket. Inside the bracket I get pn minus 1 qn minus pn qn minus 1, which is, as you know, minus 1 to the power n. So I get this expression. And perhaps you think like, okay, so what? Well, actually it's quite a big thing actually. If I bring out here qn squared, so if I do everything in absolute value, because I want to show that we have convergence, I want to do much more. If I do qn outside here and multiply it by that, so if I do like this, let me just write it out. If I do like qn squared times x minus pn of qn, I get something in absolute value, which is like tn times applied to x, which I denote like tn. And here I get 1 plus tn times qn minus 1 over qn. And it's actually really nice to look at what this is, and that's what I'm doing on the next slide, because this qn, I had a recursion relation for it. It's an times qn minus 1 plus qn minus 2. So if I divide numerator and denominator by qn minus 1, I get, this is going to be an, 1 over an plus the same expression with an n a little bit lower. So I can repeat this whole thing, and I find actually that qn minus 1 over qn is 1 over an plus 1 over an minus 1 plus 1 over up to the beginning. And this is what I call Vn, as long as n is greater or equal than 1, and V naught is 0. And you might think like, so what? Well, you know, there's a reason why we call this Vn, because this is the digit you just saw at time n. And the moment before was this digit, and the moment before was the next one. And at the beginning of time, when we started, it was this digit. This is the starting digit of x. So this is like the past at time n, that's why it's a v. Well, it doesn't make sense to you, but it's the v of the Dutch word verleden. Couldn't help it. And of course, with the future, you can also do something. The t is a kind of shift map. And so tn starts with an plus 1 and then an plus 2. So the t is still coming from the Dutch word toekomst, future. So at time n, this tn is like the future at time n, this vn is the past at time n. So if you want to understand really these things, these numbers, then you need to know about the future and about the past. You need both future and past, and the natural extension is sort of giving you that. And these numbers, well, they are sort of important, so that we call them approximation coefficients. By the way, note that these guys, they grow like exponential, at least as fast as the Fibonacci number. Tn is a number between 0 and 1, Vn is a number between 0 and 1, so this is smaller than 1, of course it's larger than 0. That means that if this raises to infinity, this raises to 0, so you do have convergence, very fast convergence. So that's one of the reasons the fractions are interesting. So that's why we sort of look at these things. and we're not the only ones. It already started with Legendre, who said, okay, suppose I have a number x and some rational number p over q in lowest terms, q positive, and let's assume that in fact such a theta, so x minus p over q in absolute value is smaller than a half times 1 over q squared. I put the q in front of the x minus p over q, but okay. Suppose we have this. What do we know? Well, something spectacular. This p over q is a regular convergent of x's. So if you expand x as a continued fraction, one of the convergents will be p over q. Right? So there is an n, so that p is pn, q is qn. That's nice. So if you really want to be close with a rational number to an irrational x, it also works for rational x, but then it's not so, yeah, it's only finitely many. But if you have an irrational x and you want to be really close to it, you're sort of bound to use the convergence. And this was something already known to Huygens. He lived very close to Delft. Perhaps I pronounced the name in a way you don't recognize it. Christian Huygens. At some point.
So what is regular in this context?
This is what is called the regular continued fraction. It's just called like that. Yeah, that's kind of standard name, or simple continued fraction. That you always will have, so you can always continue.
I understand it's a regular convergent.
Yeah, so it's a convergent coming from the regular continued fraction expansion of x by truncation. Yeah. And the regular expansion only has these 1 over, etc. the whole time. We're going to do something about it in a moment, if I don't talk too much. Okay, this is what I saw. This theta n is Tn over 1 plus Tn Vn. Oh yeah, I was saying about Huygens. At some point, he was I think the first president of the French Academy of Sciences, and his father was a Dutch diplomat. And at some point, Holland was at war with France. And just before that, the Prime Minister of the Sun King asked Huygens to build, as a present for the king, a kind of model of the universe, of the sun and the planets around it, the planetarium. And of course that's a clock, right? The planetarium is just a clock. It's just things moving. So what Huygens needed was rational approximation of the orbits of the various planets, and then he said, yeah, I need to have continued fractions. Not too many teeth, not too few teeth, etc. This thing was actually built, was never given to the French, because we were at war. So it's still in Leiden in the museum. It's actually just like a box, so most people think, well, doesn't mean a thing, but it's actually quite nice. So already Huygens, who was at the time of Newton, worked on these continued fractions. Okay, now this is already mentioned. This is the future, the Tn, this is the past. But there is something else which is nice. Of course, this is just the same thing. If theta n is Tn over 1 plus Tn Vn, then if I go one click back in time, Tn minus 1 is, of theta n minus 1 is this fraction. Let's see, is there something to erase the blackboard?
So there's this green.
Oh, that's for the erasing? Okay, great. Okay, so I have Tn minus 1 here, and I know that Tn is actually Tn times applied to x, is actually T applied to Tn minus 1 times applied to x. I told you, it's very trivial. And this is this Tn minus 1. So this is actually 1 over Tn minus 1 minus An. So if I bring the An to the other side, put things upside down, I find Tn minus 1 is 1 over An plus Tn. So I can plug it in. So if I do that, let me do that. I mean, it's anyway an easy talk, so might as well keep it easy. I get 1 over, so this theta n minus 1 is going to be 1 1 over an plus tn. And here I have 1 plus 1 over an plus tn times vn minus 1, which is qn minus 2 over qn minus 1. Now multiply top and bottom by the same thing, so I get this going to be 1 over an plus tn plus, this disappears, qn minus 2 over qn minus 1, which is qn minus 2 over an minus, yeah. Did I make a mistake? Yeah, that's correct.
Qn minus 1 into the later there.
Yeah, qn minus 2 plus qn minus 3. That's not what I want. Shoot. I should look at my notebook. Well,
What do you think? So that an plus tn just cancels out there?
you know, let me see. Perhaps you should keep it like this, but multiply everything with qn minus 1, and here qn minus 1. Ah, this is better. Okay. So why is this a nice thing to do? So I have here qn minus 1. I have here an times qn minus 1 plus qn minus 2, which is qn, plus qn minus 1 times tn. Ah, okay. And now I divide by qn minus 1 here, I divide here by qn, this was qn minus 1. No. Ah, yeah, qn over qn minus 1. And this one also disappears. So here I get 1 over, here actually, I have 1 over Vn plus Tn. So this is actually Vn over 1 plus Tn Vn. This is what I wanted. Because now I see, that's here, is both theta n and theta n minus 1 depend on both the past and the future. Yep.
Tn, you wrote this formula, so this is how do I read it? It's infinite?
No, why is it infinite?
Because there are Tn, the first line.
Yeah.
What does it say? No. The first,
Oh, here.
yeah.
Ah, this is the regular continued fraction expansion of t n times applied to x. So if I do, okay. What did you ask?
So that's a number or it's a
Definitely.
sequence number?
Yeah, well, you should read it as a number.
So this is the conversion.
No. So if x is like this, then the t of x is going to be, it's just a shift, a2, a3, etc. Because the t of x is 1 over x minus a1. 1 over x is 1 over a1.
Yeah, but still, I was confused about the fact that we repeat an plus 1, an plus 1. That must be a mistake.
Oh, there's a typo.
Yeah.
Oh, yeah, sorry. Yeah, this is a
So I was
typo.
kind
Yeah,
of
that is.
mystified by that.
Yeah, I can imagine. This should be a 2. Sorry. Oops. I cannot change it right now, otherwise I would have done it. Yeah, no, that's a stupid typo. So probably earlier already was the same typo. But anyway, this is very nice for us. And actually, so what you want is like a space where you have the future and the past. And the future, the T map doesn't have a memory. If you apply it, A1 is gone. If you apply it again, A2 is gone, etc. They're just gone. There's no memory. And this sort of gives you a memory. Now you might think, who cares? Well, I will give you a conjecture, which has been proven, by the way, in which you both need future and past. And this is the natural extension by Nakada. So for the moment I just treat it as a dynamical system. So it's just on 0, 1 by 0, 1. On the first coordinate it's just a regular continued fraction map, so 1 over x minus tau j of 1 over x, if x is not 0. And on the second coordinate here you sort of keep track of the past. So this will be a1 if you start at level, if you start with x. The 1 over x will be a1. And if you apply it again, it will be 1 over a2 plus 1 over a1 plus y, etc. So this coordinate is going to keep track of the past. Now you might think, why do I need that? Actually, Nakada did much more than just introducing this. He showed that this whole thing is an ergodic system, actually much stronger mixing properties. And he actually found invariant density of the T-invariant probability measure, could say two-dimensional Gauss measure. And actually, if you project down on the first coordinate, then you get this as a density, and actually this was sort of used in this paper from the 1950s by Hitoshi to get all these classical results by Levy and Hinchin and others using the ergodic theorem and using this invariant density by Gauss. So this was actually a groundbreaking paper. Okay, the only not so nice thing about the ergodic theorem is that you lose sort of feeling of what the speed of convergence is, but you can show what the convergence is. And this paper was a game changer. Why is it nice to have the natural extension? Well, usually the invariant density is of such a form. So it can be really difficult, one-dimensionally, two-dimensionally. Usually it's easier. And then by projecting, you get the one-dimensional invariant. And okay, this paper was from 1981. Perhaps at that time nobody was really, and Nakada really showed that what he built is indeed a natural extension, because anything isomorphic is also a natural extension of what Hitoshi studied. And so it's an invertible system containing the original system by Hitoshi as a factor, and it's the smallest one. That's an inverse limit if you want. Okay, why was this interesting at the time? Well, at the time Hendrik Lenstra was still in Amsterdam, and he was doing primality testing, and that for primality testing he also used continued fractions, and he got a kind of conjecture. And later Marius Josifescu found that actually Döblin already had this conjecture just before the Second World War. So, but a lot of things Döblin found sort of disappeared for a long time and then finally came back because archives were opened, etc. So what does this conjecture state? It says this limit, so I count how many times from 1 to n is my approximation coefficient of my number x more or equal than z. Z is a number between 0 and 1. Well, this limit exists for almost all x and it's equal to some distribution function. And this distribution function is linear from 0 to a half, it's z over log 2, and then slopes off. So it looks a little bit like this. And the reason why it slopes off is easy to explain in a moment. So let's now pose this question to many people, among whom my PhD advisor. So it looks like this. It's linear, and then it slopes off. And he asked many people, and then at some point, Jager, my advisor, saw the paper of Nakada and thought, whoa, that's it. You know, I simply need the natural extension. Other people also tried to prove this conjecture. Donald Knuth tried, and he tried to do it by a kind of Gauss-Goodwin-Levy approach. But what was really hindering him to get this result is that you need knowledge about the future and the past. That's the point. If you look at this natural extension, and if you look at these curves, so let's say Tn over 1 plus Tn Vn is some z. Well, how do they look? Well, they look like this. if z is smaller than a half, they go through this point and through a half if z is larger than, if z is exactly equal to a half, and they look like this. And what was the idea, what Jager had? He said, well, let's start with the point x0, that's t0, v0, apply t to it, then I get t1, v1, apply t again to it, then get t2, v2, and go on like this. So starting with some point x, you walk around and you just, let's say this is the thing I'm interested in, you just count how often you hit this region. Oh, you would say this is just a simple application of the ergodic theorem, right? Except that you start with 0, and if you want to apply the ergodic theorem, actually this should be xy, kind of typical point. So the proof is of course the ergodic theorem, but more to show that this point, the orbit, starts to behave like the orbit of a typical point. That's the proof. So that was nice. And then, then I sort of started my PhD work, and I thought, wow, we didn't really look at a map like this. So I thought, exit the clean lens now, but let's look at this. Why would I look at that? Because I had theta n minus 1 was Vn over 1 plus Tn, and theta n is Tn over 1 plus Tn Vn. So it's sort of natural to look at a map like that. And if you do that, and you say, okay, I'm starting at 0, 1 by 0, 1, and I'm applying this map psi, what do I get? Well, I get a triangle, 0, 1, 1. So if I start with the point T and Vn here, this is going to be mapped, this point is going to be the psi of T and Vn, the future and the past, which is going to be my theta n minus 1, theta n. And you see right away, this is line alpha plus beta is 1. I see right away that theta n minus 1 plus theta n is smaller than 1, of course, possibly. So I see that the minimum of two of them is smaller than the half. Okay? Well, that's a classical result by Valen. So, but that's for free, more or less. And then you can do many other things, of course, which I'm trying to explain now very briefly. And you could also say, okay, go back. Look at the inverse. It exists, it's a very nice map. Why would I like to do that? Because then I have more control of what's happening. So, just to give you a little bit more structure, this region 0, 1 by 0, 1, I cut it up in regions where the digit is 1, 2, 3, 4, etc. Make it longer. It will also be on the slides. So, this is 0, 1 by 0, 1. This is a half, here is V1. So, these, all the points which are in here, the first coordinate starts in the continued fraction expansion with a 1. Here's V2. It's 1, 1/3 to, here's the, so if I have a point xy in here, let's say in VA, then I know that x is, its expansion is going to be a, and then the rest I don't know. And the y is free, and like that. And why would this be interesting? And by the way, you can also, V is for vertical, you can also look at horizontal strips. You can show that actually, if I take the mirror image and reflect them in T is V, I get from one to the other, or if I apply T to it. And I have what I just said, if T n times applied to the point xy, if it's in VA, then the next digit, because on the first coordinate I will have T n times applied to x, so it starts with a n plus 1, is going to be a. And the same, but then in the past, with this guy. It's going to be in the vertical strip, if what I just saw was an. Now you might think, why is it interesting? Well, it's because, for instance, this strip V2 is mapped to this thing, It's not a rectangle, but a quadrangle if you want. This thing, the psi of V2, and V3 is mapped there, and V4 is mapped underneath it, etc. And you might say, why is V1, its image is a triangle? Well, it's because, you know, these lines like this and this, here they sort of meet. So it's actually also a quadrangle with, to the point of half a half, but then these have the same slope. Okay, so why is it interesting? Well, suppose I have a point here, let's say in this thing, and then I know my next digit is a 2. I go back, I go here, I can apply the continued fraction map, the natural extension map, and then return there. Aha! So I can sort of do this. And why is this interesting? Well, because if I start in the point here, then I can calculate that it's like this. No, that's not so trivial to see, but it's more important that I start with a theta n minus 1 theta n, and then go back, use the continued fraction map, and then return to the triangle. I get theta n plus 1. So the next approximation coefficient is the function of the previous two. It's this function, automatically. It's the second coordinate function of f. Aha! So it's like this. So if I know two approximation coefficients and I know the digit, and so if I know where it is in this rectangle, in these rectangles, then I know the next one. So that's sort of nice.
Excuse me, I'm a bit lost. So could you remind, so T is a kind of shift map on pairs xy, right?
Yeah.
And what is psi?
Psi is just this map, like this one, to go from 0, 1 by 0, 1 to the triangle. So the psi of xy is y over 1 plus xy, because this would be t and vn, this would be theta n minus 1, and this would be theta n.
I see.
That's the way, the reason to do it.
So just kind of change the coordinates.
Yeah. So it's sort of neat. And then you can look at this map and you can take the derivatives. Well, the second one is negative, that's very easy to see. The first one is a little bit work because you almost touch a strip. Why is it interesting? Then you might think like, well, I mean, whatever, really. Why should we do this? Well, you know, on VA, so let's say V2, here, this two-dimensional continued fraction map has a fixed point. Namely, the point which is mapped, which has continued fraction expansion, let's call it psi A, just A repeatedly. So this is a quadratic irrational number. You can actually calculate it, and that is kept in place by the map T. Let me recall you, the map T is fine. It's just T of x, and here it's 1 over the digit, let's say a1 plus y. Well, if the digit is a and y is 1 over a plus 1 over a, it's fixed. It goes to itself. And this point is mapped in this triangle to the point, which is quite nice, 1 over the root of a squared plus 4. So I get now a very cute situation. Suppose I know my next digit. So I know in this triangle where I am. So this is a half. First, third, etc. Suppose I'm in this one. This is the psi of V2. I know this fixed point is somewhere on the diagonal, so somewhere here. And I can look around this diagonal. Now suppose, if I blow it up a little bit, suppose I have a theta n minus 1, that's the first coordinate, and a theta n, which are both larger than this fixed point. Well, because my function is, has a negative derivative towards x and y, so I'm here somewhere with theta n minus 1, theta n. In order to go from here, from the fixed point to that point, I have to go down and down. because the derivative was negative.
Excuse me,
Yep.
just there was a question from online audience. Please, could you remind us what is the theta function?
Theta. Yeah, sure. Gotcha. So the theta function is theta n is qn squared times x minus pn over q. So, of course, this will become very small, this will grow very fast, but this is still smaller than 1, and of course positive. And, okay, Valen showed that if you have two consecutive ones, at least one of them is smaller than a half. And now I'm going to show something more, but if you go down and down, then you see that the theta n plus 1 is actually smaller than 1 over this root of a n plus 1 squared plus 4. I mean, in one of these strips where you know what a is, it's the next digit, a n plus 1. So it will be less. So if they are both larger, I'm above it, I'm to the right of it, the next one will be less. If they are both smaller, let's say here, and in order to go there, I have to go up and up. So the next one will be larger than 1 over the root of a n plus 1 squared plus 4. So I have found actually something which was found many times by many people. Well, this was only found by one person, by a guy called Tong, Jing Chen Tong. This was found by many people, like at least 3-4 times. It has been published by several people. Usually it's a lot of work to get this, but it's more or less trivial right now. So you see that the minimum of 3 consecutive thetas is smaller than 1 over the root of a n plus 1 squared plus 4. And note, a n plus 1 is 1 or more, so this is going to be smaller than 1 over root 5. This is a result of Borel. And yeah, this guy says, this result says, yeah, it cannot always be Christmas. So you also will have one which is relatively not so good. And so if you have a gigantic partial quotient, and for almost all x this happens quite often, then this is actually saying that the minimum of these 3 is an incredibly good approximation. Okay, and that's Borel. Now, of course, for a long time I thought, what can be said about this? Not much. And then somehow Arena and I started to look at Valen because this is Valen, the minimum of 2 consecutive is always smaller than a half. Because we read a paper, or several papers, first by Hanschel, and later by Hanschel and some co-author and another person. And there's also a paper by Hanschel and Kidner on the Borel thing, but I think that's harder. Anyway, Hanschel proved that x minus p over q, if p over q is either this converted or the next one, is always smaller than, well, it's 1 over 2 plus etc. times 1 over q squared. So if q is big, this is more or less a half. So it's just, it's a little bit more than 2, so if you divide by it, it's a little more or less a little bit less than a half.
Excuse me,
Yep.
P and Q are between here, or?
P and Q are, P is like this and Q is like that, or P is like this.
I see.
Yeah, this is literally copied from the paper, by the way. And so when we saw that, we thought like, we can do better, right? I mean, I wouldn't have thought about Valen, to be honest. But since he has several papers on this, and yeah, I thought I didn't really like the result because you know, Qn is growing really fast, right? It's growing at least as fast as the Fibonacci numbers. So if I take, for instance, the 15th Fibonacci number, Q is already 610, and this is really the slowest you can go. This HQ is almost a half indeed. So it feels like, can't we do something else that we can improve it instead of this improvement? And then I thought, well, perhaps we can use this setup. But before we did that, I also thought like, perhaps it's not even true always. And so perhaps there are cases that his result is not always true. I mean, if I go back to the natural extension, look. So this was, here's a half. If I'm close to 1, how does my number looks like? So if, let's say my x is close to 1, I know the first digit is 1, because I'm in a half 1. But then the second digit, let's say, call it d, if here is 2/3, 3/4, 4/5, etc. So here we have digit 1, 1, here we have digit 1, 2, here we have digit 1, 3, etc. So if I'm close to 1, this second digit is going to be really big. And if I can force that I have a point for which the y also is close to 1, I will have the same effect. So that's why Rina and I looked at the following thing. We said, well, let's just look at this rational number with only 4 partial quotients, d, 1, 1, d. And the d is at least 4, but can be any positive integer. Then we have that the h of q1, this Hanschel number, is smaller than the corresponding theta. And the h of q2 is also smaller than the corresponding theta. That's not really what the theorem said. At least one of the two should be smaller. That is a little bit annoying. And so somehow this point, you start at level 0 with 0d, 1, 1d, then you apply t to it, you apply t1s to it, so t2 is going to be the number 1d. And v2 is, by the way, the same number because of the shift. You apply t one time, this d went to the past, you apply it another time, this 1 went to the past. So you get this 1 over 1 plus 1 over d, which is this guy for the past. So this point is really close to this point 1, 1. If d is large. Well, large is, well, it's enough to be larger or equal than 4 already. Okay? Now, how did we prove it? Let me just blow through it because it's just a by result. The theta 1 and the theta 2 are both the same, because they're the same number. And I can calculate it. It's theta 1 is theta 2 is d times d plus 1 over, let me write it out. D times d plus 1 over 2d squared plus 2d plus 1. Okay, why do I write it down? Because I want to this is how the number looks like, this is how you get the convergence. The first few are obvious, but you can just write them out using the recurrence relations, it's very easy. I will prove the second statement, the first one is easier. In the second statement, note that q2 is d plus 1. So if I want to replace d here, I have to replace it by q minus 1, that's why I wrote it down. And I want to show that this number is smaller than, well, d replaced by q minus 1. So I get q times q minus 1, etc. Now, this is trivial. This is 1 divided by this number, so I do cross multiplication. Note that I can bring a 2 out here and I can bring a q minus 1 out here. So I get 2 times q minus 1, and what is left is q minus 1 plus 1. That's this one. And then, yeah, it's still this plus 1, okay? Now, why is it nice? Well, I can divide out this, so I get 2 plus 1 fraction is 2 plus another fraction, and then you can just rework it, and you see this is the same as 5 times q is smaller than q squared plus 2, which works for q is 5, or more. So d should be at least 4 or more. And then bang! The second statement was gone, and the first one is easier. So, so we really were sort of motivated to really look at these things. How can we improve falen? Well, we said let n be the minimum, of an and an plus 1, and capital M the max. And we had to look at two different cases in order to prove Valen's result. The first result is if M is greater or equal than 2, and in this case we have a subcase that the small m is also greater or equal to 2 and equal to m. And then, well, it looks horrible, but the minimum of 2 is smaller than this number, which is by far smaller than 2/5. If m is 2, it's 2/5. And the max is not so important, but it's this number. And in case m is strictly smaller than capital M, we have that the minimum is smaller than this. And it can be 2/5, by the way. And the maximum is also. And yeah, how is it proved, really? Well, let me go back to this drawing. So, if this was 0, 1 by 0, 1 in Nakada's natural extension, then this was V1, this is V2, if this is a third, this is V3, this is a quarter, etc. And the H were like, this is H1, this is H2, this is H3, horizontal, and they are mapped to the triangle in a similar way. Now, suppose that my capital M is larger than my small m. That means that I was more, here's the diagonal, of course, I'm more under the diagonal than, well, it can also be flipped, but just to make things clear, I sort of made this smaller than the other one. So here, the M is, the capital M would be 1, 2, 3, 4, it gets thinner and thinner. That's what I suggested with this drawing. And this is mapped to something like this. Now, if M and capital M and small m are the same, then this is really a symmetric picture, and it lays on the diagonal. So it looks like this.
It looks like an affine map, is it?
Yep. No, it's really nice, no? So it's really like this is capital M and small m are both 2, and here they're both 3. And it's really, you're in this region then, and then in this region or in this region, etc. So you see, oh, if the theta n minus 1 theta n is here, it has the minimum is smaller equal than the value in this point, and the maximum is greater equal than the value in that point. And if they're different, then you have symmetry, you only need to look at one side, then the capital M is 3, small m is 1, that everything is determined by this point, or you flip it around. But the only difficult part is really this part, when both an and an plus 1 are 1. And that looks like shoot, because here's the point of half that gives Valen. There's no improvement. So in that case, that's why we said we had an easy case and a difficult case. We have to sort of start to look at this region. And that's what we did next. And then we got this result, which looks like somebody vomited over the blackboard. Sorry, it looks a little bit horrible, but I mean, no, it's not so bad. But what was the idea really? Well, the idea is the following, and if you see this picture, it might perhaps not mean anything to you. Let me make a new drawing. You see, so if this is 0, 1 by 0, 1, this is a half, this is a half. I know that my next digit is 1 and my previous digit is 1. The next digit is due to this. Now let's just look at this guy, the V1. Okay, what do I know? I know that if this is 2/3, 3/4, etc. Here the digit is 1 and then a 1. Here the digit is 1 and then a 2. Next is 1 and then a 3, etc. So I can look at where is this line going, where is this line going, where is this line going, etc. And they're going, well, the most left-hand one went here, then here, and here, etc. It fills this up, and this point moves to a half. So it stays underneath this dotted line. So all these lines, and note that sort of tells you what is the, not an plus 1, but the an plus 2 digit. It's going to be, well, here it's going to be 1, here it's going to be 2, here it's going to be 3, next one 4, etc. So it gives you an enormous grip of where you are, and then you sort of see also that your point k to n minus 1 k to n is sort of blocked away from a half a half. Okay, it moves of course in the limit to a half, but it would mean that the next digit is really incredibly big. Okay, that could happen. But you know, my point was that Henschel and his co-authors, they needed to look at the Q's. So the whole prehistory, I only need to look at one point in the future to know, it's actually staying away from a half or not. And you can also look at the vertical one, just to block out more. So an minus 1. These comes from the to cut this up. So so this is 2/3, 3/4, and then this line and this line are really these two. So if you have these two, you have much more control, and that's why we found this result. Okay. Now, how long do I have actually, or did I totally weigh you out? Okay, now I want to talk about something else, because this was sort of, no, not easy, but a lot of things in a way, but also would like to show you another application of natural extensions. And this is actually very old work by myself, which was published in an implant journal, by the way, in arithmetic, when I was still young. And what is the idea? Well, there are very many continuous fractions. There are regular continuous fraction, but you have integers, diagonal, Rosen, very many. Is there a way to sort of connect them? Well, not always. You cannot connect the Rosen to the regular because they work on different groups. But actually, the Nakada alpha expansion, which is an infinite collection of continuous fraction algorithms, you sort of can understand them starting from the regular. And yeah, what do we use then? Well, we're going to use what is called an induced transformation. And yeah, what was the key observation? This is something from one of the two books by Perron. If I have a continuous fraction expansion, you should read it like this is what's before, then the digit is a plus 1 over 1 plus, and then the digit is b, and then the rest. I sort of can get rid of this 1. I can kill it. I can make this expansion one click shorter. By sort of saying, okay, I want this out, so this will become a plus 1 plus minus 1. Oh, that's already, it's not regular anymore. Plus b plus 1 plus, and then the rest. So I can do local surgery. So I can change it locally. You can make it one click slower, shorter. Now you might think, okay, so what one thing? But if you do it infinitely many times, then I can kill the 1s. And for almost all x, about 41% of all the digits are 1, so I can kill a lot of 1s if I want. I really gain speed, so to speak. And so one singularization is not so interesting. To knock out this one is called singularization, but if you can do it with a lot of them, well, I'm not going to show it, but then what you throw away is regular convergence. So you get like a subsequence of the regular sequence, so you go faster to your goal, so to speak. That's the whole idea. Okay, and it's not a regular. And you can never singularize two consecutive ones, because if you kill one, the next one will become whatever it was, plus 1. So it's at least 2, perhaps 3 if not a neighbor was killed. In my setup here, you can only singularize once, but there's a recent paper by Slade Sanderson and Parmigiani and myself that we have an even higher point of view. We start with the fairy map. But in this case, only once can be killed. And then, yeah, you could say, okay, can you give me an algorithm? Well, that would do some stupid terminology. Suppose I have a block of ones. By this I mean the first digit was the A1, or it's some AK, but then the digit before it is not 1. It's AK minus 1 is 2 or 3 or 4. It's just one block, and behind it, if it's an input block, of course, there's nothing behind it, but if it's a finite block, behind it is the next digit is not 1, before the next digit is not 1. Why do I want this? Well, I'm going to give you an algorithm. Singularize in each block the first one, the third one, the fifth one, etc. Okay, do this. If you do it, you throw away a lot of conversions for almost all x. And what you get is actually a new continuous fraction expansion with these minus signs, and with this, these are the new digits, bn plus the next epsilon, which can be plus or minus 1, is at least 2. Now you might think, okay, but already by Hurwitz in the 1890s it was proved that this uniquely determines the nearest integer continuous fraction expansion. So using algorithm A to the regular, whoop, gives you the nearest integer. So the subsequence, the sequence of nearest integer conversions are actually a subsequence of the regular sequence. Well, you get it for free, really. Okay. Well, I'm not going to prove all these things. Is this the only way to do? Is this the fastest way to do? Is there an underlying ergodic system? No, the only way, of course, not the only way. You can do it in many ways. Instead of doing the first, the third, start at the end, do the last one, and then not the next one, but the one before that, etc. If you have a block of even length, you would get something different, and what you get is actually Hurwitz singular continuous fraction expansion. Is it the fastest? The answer is yes. I will show you in a moment. This B is the singular. Is there an underlying ergodic system? Answer is yes. And that we will get via the natural extension of the regular, the one by Nakada. So I can do A or B. These will throw out large numbers of ones. This one, C, will not do that. This is also a classical continuous fraction expansion. This will be Minkowski's diagonal. So only singularized ones if the partial quotient of the approximation coefficient is larger than half. You can do it even differently. If you have a big block, start with the first and last and go in. And then if the block is even, there's a moment you have to choose. This will give you the optimal if you make a good choice. Well, this is what I just said. First one is Hurwitz, nearest integer. The other one is singular, and it's Minkowski. Okay, now you can have these matrices again. It's almost the same. Instead of an A naught, I have a B naught here. In the regular case, these were always ones, but the whole setup is the same, works in the same way, gives you the same results, the same relations with the ANs and the BNs, etc. And I also see that these guys are already in their lowest terms. Okay. And I have passed, the whole thing goes wonderfully well. And I can look at the approximation coefficients, and they're more or less defined in the same way. Of course, the t's can be negative now, so I need to make this positive, and this is the sign of tk. Okay, and if you can do that, okay, this is the last thing I want to tell, otherwise I blow up your head, but let me show you that with this algorithm A, there's a nice region connected, which tells you how to implement the singularization, when you have to singularize. Okay. Now, note, we singularized the first one, so if the moment before we were not seeing a digit 1. Here the digits are always 1. Here 2, 1/3, etc. But if my previous digit was not a 1, I'm under a half. So if I move in with my point Tn minus 1, Vn minus 1 into this region, because I have a digit 1, I'm moving in under this line. I'm moving in into this region. Now suppose I have an enormous block of ones. This region is mapped here. This is 1 and half is going to 2/3. If I have a lot of ones, I'm here somewhere. I will be mapped here. So in this region. And then I'm going out, I will be mapped there, and then mapped here. And if you will look at it, you will see actually these are Fibonacci numbers, and this whole region is converging to the golden mean. So I get like, this is the region I want for this nearest integer algorithm, for this algorithm A. Singularize if and only if T and Vn is in this region. That's the whole idea. Okay, now, from here, you can say, okay, I want all the regions. For instance, the singular would be this region. This is the golden mean. Note that this block is actually moved by the natural extension map to this block. So they really have the same mass, same measure. If you have another singularization area, just choose something. Let's say this is SU, S upper and S down. Because I can never singularize two consecutive ones, this S down must be mapped here, this joins from SU. So you see the measure of SU and the T of S down is smaller or equal than the measure of the nearest integer region. So it's the fastest, you cannot go faster. And well, from this point, you start to build the theory. Now, I'm not going to tell you more because I think I will blow your minds with all these trivial things. But if you have questions, please shoot. Yeah?
So I wonder, have you tried to generalize the result about minimum of status for longer strings? For instance, if you take 4 consecutive status, can you say more about this minimum or maximum?
I never did that, to be honest. It looked very complicated. But we started to look at it, Irina and I, because you see, if you want to improve on Borel, perhaps you can recall, I was on this region, right? Here somewhere. And then you want to improve on this, and yeah, then you need to know more and more of the past. So you need to do more and more like what Hansel and his co-authors are doing. So you need to get a better grip if you have more digits and more approximation coefficients. But it's sort of really slipping through your fingers. It was nice to do the Valen because we were cutting this up, you know, like this. And the larger the digit, the more you walked away from. You see, it's sort of now it's actually inside this region, in the region 1,1, and it's sort of shrinking towards the golden mean, the point golden mean. So it feels like, in that sense, the approach of Hansel and his co-authors might really be right. Yeah, but it's a sort of difficult thing to get your fingers behind. Yeah. By the way, if you do this, you get a natural extension of the nearest integer, for instance. It was already found by Nakada. You get it by singularizing, right? So you can think, do we have like the minimum of 3 consecutive is smaller than 1/√5? The answer is no. Because you threw away actually relatively good conversions and you kept relatively bad ones. So there's a result by Tom which states that that can be really a long string before it's smaller than 1/√5. I mentioned in the optimal, which is also S expansion, actually the minimum of 2 consecutive is already smaller than 1/√5. So you sort of singularized in a good way, you sort of killed off in such a way that the bad guys disappeared and the relatively good ones remained. Question?
I have another question. So,
Sure.
in this software you use singularization. So the result in kind of continuous fractions with absolute plus minus ones can be obtained as application of alpha ground function. I mean,
Alpha continuous fractions.
yes.
Yeah. These are all examples of this. So the Nakada ones are all examples. So alpha is a half is this region. Alpha is the golden mean is this region. In between you get a mixture. If alpha is between a half and 1, if alpha is smaller than a half, then it becomes much more difficult. Then what you also get are median convergence, and they're not in the regular convergence, so you have to sort of bring them in by local surgery. So this approach, local surgery, works, and if you start with the theoretical region, you can sort of transform it to an alpha region. If alpha is between, let's say, root 2 minus 1.5, that still looks okay, and also a little bit smaller than root 2 minus 1. But then it starts to look very wild and very difficult. And actually, you already know that it will be difficult because there's this paper by Lutzi and Marmi where they look at the entropy, right, of these maps. And to the left of the golden mean squared, so 0.38, the entropy behavior is very wild. I mean, if you look at the entropy map, it looks like this. Like if this is the golden mean squared, I have no idea what the value is, but it looks like this. But actually, if you zoom in, then you see the parts it's horizontal, parts goes up, and parts horizontal, parts goes down, etc. It has a very wild behavior. So this was studied by Lutzi and Marmi, and by Nakada, Marmi, Lutzi, I think, and Natsui, and other people. Wolfgang also looked at it, Wolfgang Steiner, who gave a talk not long ago here. And Wolfgang works on everything, so.
I have a question.
Yeah, sure.
So when you were discussing the natural extension of the Gauss map, so this not Nakada's map.
Nakada came with this, and later he looked at another version of it, an isomorphic version, which he thinks is better, and I disagree.
So you mentioned that you can prove that a typical point in the base, so typical point of the for x0 behaves like a.
No, it was not me, it was Jager.
Right.
It was by Jager Wiedeck.
So my question is it difficult to see?
No, it's very easy to see because if you have a starting point, let's say this is my starting point x0 and here is some other point xy. This point is moved under the T-map to one of these strips. And then again and again. And so they move together and they sort of, the second coordinate is pressed together. That's the idea.
Okay.
So it's like a shadowing going on.
Okay.
Yeah.
Yeah. Thanks.
Yeah, it's not a trivial thing actually, to be honest. Yeah, so at first the proof was quite nasty and then later Jager jazzed it up a little bit. Yeah, this was before I started these things. So, no question?
I have a comment, but I don't want to keep everybody here.
Yeah, sure. You can leave if
It
you
will
want.
be a private comment.
Okay. This is a cliffhanger.
No, it's just it's ex-prompt. I haven't prepared it.
Sorry?
It's ex-prompt. I haven't prepared the talks.
Oh, okay.
Keeping everybody so that I struggle to tell you something and it's not a good.
Okay. Oh, cool.
Questions from online audience?
No, no question.
Oh, there were quite a few questions during the.
Yeah, that's true. Sorry. Okay. Well, thank you for inviting me.
So, we can talk right now?
Yeah, sure.
Okay, so I published two papers 15 years ago with the collaborator Siemaszko. My name is Wojtkowski. Probably you don't know my